Hello, everyone. Thanks for joining. This is the CIR Talk series. My name is Zamani, and it's my pleasure to introduce Arman Cohan from Yale University. He's an assistant professor at the Department of Computer Science. Uh, he publishes a lot in NLP and IR conferences. He used to be a research scientist at AI2 or at Institute for Artificial Intelligence, and he's still a faculty researcher there as well. Um, his work has been widely cited. He has received multiple awards, including a Best Paper Award from EMNLP, an Outstanding Paper Award from EACL, a Honorable Mention Award from Colink, and the list goes on. Today, he's going to talk about placing the puzzle language models with multi-document contexts. So please join me in welcoming Arman.
Thank you so much for the warm introduction and for inviting me. It's my pleasure to give you some of our recent work on multi-document modeling. And yeah, I wish I was there in person. I know Yale is very close to UMass, so maybe in future we can have another talk in person. But for now, let me get started and tell you a little bit about multi-document modeling. So there are many practical problems in NLP that are inherently multi-document. In this type of problems, you usually have multiple documents where the information that you want is kind of scattered around, and you want to ideally locate this information and aggregate them across a wide range of different documents. And a good example of this is just literature reviews. We all see these survey papers or reviews that go through a lot of different papers, and they summarize the main findings and results from these papers. And this is a very difficult problem currently. So on the right side, there's a figure I borrowed from this paper that shows essentially there's like a 10-year gap between when a review article is being published and when the actual study is being done. And this is actually the case in biomedical domain, and like collecting and aggregating all these results from these papers is very difficult and labor intensive. Another classic example of multi-document modeling is like claim verification. You usually have claims like this one, for example, the COVID cannot thrive in warm climates. And then you want to know actually if this is true or not. So you have a retrieval system that kind of first retrieves all the documents that can be related to this claim, and then some of them refute the claim, some of them support it, and then you want to kind of come up with a general statement that tells you the summary of how the research looks like on this specific claim. And there are other examples. For example, legal case summarization. You usually have a lot of different, for example, papers, transcripts, legal briefs, statutes, and other notes that you want to summarize all of them into a single coherent report. And news aggregation is actually another classic example that you might have a lot of different articles about the same event. Each of them have their own political orientation and biases, but you want to actually aggregate everything that you have about this. So this talk, I'm going to tell you a little bit about how we can have better language models for doing this type of tasks. Then I'll talk a little bit about the role of retrieval and open domain summarization. And finally, I'll talk about some of the benchmarking work that we've recently done. So first about modeling. So if you want to do like modeling on multi-document text, there are some differences. Usually in single text, you have a lot of information that you want to connect the entities within each other or like within different parts of the paper or article. In multi-document modeling, you usually have information that can be matching other information from another document. Or you might have information that could be complementary to what other documents are mentioning. Or the information could be disjoint, or in some other cases, there might be contradiction. One document might say something, the other document might completely contradict that. So the main question that we were interested in was, can we make language models better at this type of problem? So the first work is this classic work on multi-document summarization, which we call Primera. And this is basically a training method. So the traditional methods, if you're familiar with the literature on multi-document or multi-hop modeling, usually people use some sort of hierarchical methods, GNNs, or some sort of customized architectures. However, like with long context transformers, for example, with longformer, we found that like you can just concatenate all the documents into a single long string and pass it through your long context transformer, and then it can solve the task for you. For example, it can generate a coherent summary for you. And yeah, so this type of transformers are all over. For example, we have sparse attention methods, we have sliding window methods, we have approximate attention methods. And these days, you even see that people can extend context length of transformers to 1 million tokens and beyond. So this is a pretty solved problem. However, the main question is, still a lot of these transformers are trained with the regular next word prediction objective. And the question that we're interested in is, are these type of objectives actually optimal for multi-document summarization, or can we use other types of self-supervised objectives to improve performance for this type of tasks? So in an earlier work, which we called cross-document language modeling, we showed that actually this might be possible. So this was a very simple trick. And if you're familiar with longformer, for example, or Big Bird, or this type of long transformers, usually you have different types of attention, like a global attention and like a local attention. So we showed that if in a multi-document setting, when you concatenate these documents together, if you assign global attention to mask tokens and you do the unmasking objective, then the model becomes better at multi-document tasks. And why is that? It is because when you're assigning global attention to some of the tokens, you're encouraging the model to implicitly looking at the entire sequence, looking at other types of documents when it is recovering information. And yeah, we saw basically that this kind of results in a substantial improvement over a baseline that doesn't use this type of training. So the goal was like, can we improve the capabilities of language models by some sort of task-inspired pre-training objectives? So how do pre-training objectives for a multi-document task should look like? So our hypothesis was that a desired pre-training objective should encourage the model to connect information between multiple documents. And in fact, this was also explored in single document setting, where you could use objectives like gap sentence prediction, where you select salient sentences from an input document and you call them like pseudo summaries. And then you basically ask the model to generate those instead of, like, for example, doing next word prediction. And it looks like this. You mask some of these important sentences and you ask the language model to basically generate those in the output. And this is known as gap sentence prediction. We can actually adapt this objective for multi-document tasks. You can basically concatenate multiple documents together, and this will become a single sequence, do the masking, and then this hopefully will perform better. But the main question is what sentences we should mask. Can we just use the gap sentence prediction strategy? It turns out that like a lot of prior work are using methods like centrality. For example, we can use heuristics such as the Rouge metric to find central sentences in the whole document and then mask those out because they're central. A lot of information in the document is kind of related to that sentence that you're masking. And yeah, heuristics like Rouge are used for this. However, we found that multi-document inputs tend to be redundant. You usually might have a lot of information that talk about the same thing across multiple documents. So if you use this type of centrality metric, you would prefer exact matches between sentences, and then you select sentences that are less representative. Here is an example. There's lots of text here. I don't expect you to read all of it, but just looking at the highlighted ones, you can see that the strategy of masking using centrality will select this sentence, which results in this sentence completely being masked, and then you cannot recover it anymore because it's kind of like an exact match. So we found that actually we can select sentences that best represent the entire cluster. And we used a kind of another heuristic framework that was actually based on a classic summarization evaluation framework. If you work on summarization, you might have heard about this, the pyramid evaluation framework. And the goal is to encourage the model to actually generate missing information using other documents in the input, not the same document. So how does it look like? So given multiple gold reference summaries for each input in the pyramid evaluation framework, the annotator annotates summary content units. These are phrases or clauses that are important. And then you compute a weight by for these summary content units by counting how many references it appears in. And then the score is computed by summing up these numbers. And the assumption is basically if multiple annotators find this some summary content units in multiple of these gold summaries, that should be important. Here's an example, like this is from the DUC dataset. And you can see that human annotators have identified this summary content unit that is in red, like 2 Libyans indicted. And this is mentioned in all 4 gold summaries. It means that this piece of information is very important. So it gets a weight of 4 because it's mentioned in 4 of the summaries. Then you have the other summary content unit, like 1991, that is mentioned in 3 documents. So it has a little bit of less weight and so on. So we use this intuition to design a new masking strategy. So we wanted to mask sentences that are important, but complementary to each other. And then this encourages the model to connect information better across the document. So this is exactly how our masking strategy works. We first identify entities, like instead of the summary content units, we use entities because then we can extract them automatically. And then we build this kind of a pyramid thing based on the frequency of how many times each of these entities appears in the cluster of documents that we have. And if the frequency is higher, it means that that entity is important. And then we do sentence selection, basically by looking at the sentences in which the entity appears in. And then we quantify the relevance of each sentence with respect to other documents in the cluster. And based on this, we start selecting sentences iteratively until we reach the context length of the model. And this is basically our masking strategy. So the high-level goal is, again, to select sentences that cover the most important entities of all relevant documents and encourage the model to look into other documents in the cluster when it is recovering information from one single document. So how does this work? you can compare this with like the previous approach that is basically selecting the central sentences, and that one is blue line. You can see here that based on different number of training examples, like the 0-shot, 10-shot, or 100-shot, you see that always this new masking strategy outperforms the baseline. And if you compare with also no pre-training, you can see that this type of training is actually very helpful, especially for 0-shot. As you increase the number of shots, the performance gap decreases, but it is still there. So we did more experiments on 6 different data sets of multi-document summarization, and on all of them, we see the same trends, that like this masking strategy with this type of task-inspired pre-training can help improve performance quite a bit. And you might ask, okay, this is few shot. What happens if you do like full fine-tuning? And even in full fine-tuning, if you do this type of pre-training first, you will see that you can actually outperform the state of the art, and you even it helps in full fine-tuning setting. So the high-level point is the task-adapted pre-training is very effective for multi-document summarization, and it gives us a strong 0-shot and few-shot performance. Now the question is, okay, this is great. Now we can do multi-document summarization better, but how about other tasks, like short-form generation tasks or like question answering? So we followed up with another work that kind of adapts the same general idea, but it's based on a question answering pre-training objective. And the goal is to support both short and long form answers. So the idea is you start from a set of related documents. So usually if you're familiar with how pre-training is done, people usually shuffle all the documents in the pre-training corpus, and then they pass multiple documents in the input. So our first hypothesis was, instead of that, use related documents in the context. And then we can split this related documents into a held out document and a set of other documents. You generate questions from the held out document, and you try to answer it using other documents. And although this process could be noisy, when you're doing pre-training at a scale, the hypothesis is that this is going to help the model to look into other documents in the context. So there are some details about this. For example, you can select central sentences from which you generate the questions using the Primera strategy that I discussed before. And then we answer the question using the other documents. How did we do question generation? You can use there are a lot of work on QA generation. We wanted to use a very lightweight model that doesn't that is fast and doesn't cost a lot. And because of that, we use this BERT scale model. It was called QA-SEM, and this was from a prior work. And this is basically a semantic parsing framework for question generation. So you can generate multiple questions based on this using given a single sentence. And then we found out, okay, after you generate a question, you usually, the questions that you might generate might not be a standalone. So we found that using contextualization actually helps, like adding additional context to make the question a standalone. And this was done with another model from prior work. And again, because we are doing pre-training objective, pre-training data generation, these two models were very lightweight and fast, and this was our requirement. And we generate 3 types of instances. The first type of instance is like you completely hold out the document from which you generate the question. Then you can actually include the document, but hold out the sentence from which you generate the question. And third, you might also keep that sentence, but just mask out the actual answer. And we wanted to see actually which one helps. And it turns out that like including all these types of instances, it gives us the best results on different types of tasks. And yeah, so in our final set, we included all three types of instances. So given this, we came up with a recipe to adapt these models to multi-document tasks. So the first thing is train a model on clusters of related documents instead of random documents. Then you pass this through a long context transformer, like Longformer, and then you continue pre-training with a relatively small budget. For example, we use only 200,000 clusters of documents. And this can be done in 1 day, which is doable with like most of the academic budget. So this resulted in a model which we called Camden. And we saw that this type of pre-training objective actually helps us in different types of tasks, including multi-document summarization and query-focused summarization. In addition, we found it to also help with QA tasks like multi-hop question answering. And yeah, we were actually able to get a state-of-the-art results on WikiHub exact match in the same size of models. And we also compared this with GPT-4 to see, okay, is this type of task-specific pre-training really helpful compared with like much bigger models? And we saw that actually, yes, it can significantly outperform GPT-4 in terms of like automated metrics. And in terms of like human evaluation, we found that this method actually improves over GPT-4 in terms of content and non-redundancy metric. But what is GPT-4 better at? It's like readability and grammar, which is kind of expected. Like GPT-4 is generally very good at generating readable content. So this type of pre-training objectives can help us achieve strong results on diverse multi-document tasks. But one question that remains, and we didn't have the budget to explore, was do multi-document pre-training objectives actually scale for larger models? Does it matter if you have a very big model? Do you still see such big improvements? We think yes, at least to some extent, because our initial comparisons with GPT-4 were very promising. However, it's not conclusive. Like we ideally need someone from industry to do this type of experiments. And this has some kind of connections with non-parametric models where maybe including related documents in a context can help you do future learning much better. And there are actually newer papers coming out to support this hypothesis as well. So yeah, now let me talk about a little bit about another concept, which is open domain multi-document summarization. So far, we've seen the regular multi-document tasks where you have multiple documents and then you have a summarizer, and then the summarizer generates a summary for you. However, and an example of this is systematic reviews. However, the first thing is such input documents need to be defined and collected in the first place. And this part might be more interesting to folks working on IR. So this is where the role of IR becomes more important. Most of the existing work in multi-document summarization assumes that the input document is already given and it's like a very high quality, both at training and testing time. However, in many applications, you know that these documents would be defined by an information need, and this information need is kind of expressed as a query by the user. So you usually issue this query to a document index, you get these documents, and then you pass it to a summarizer. And this is like the full system of an open domain setting, but for summarization, where you want to generate some sort of summary starting just from a user query. And this is kind of a little bit different than the classic IR, because in classic IR, the goal is to rank documents that best describe a query. However, here, like we want to go all the way down to a summary that briefly describes what a user wants. It's kind of more like retrieval augmented generation. So our question was, given that even state-of-the-art retrievers are imperfect, what happens if these input documents that you give to summarizers are not perfect? What happens if they contain errors? So these are the questions that we were interested in. The first was, how does the end-to-end performance impacted if we have imperfect retrieval? And what type of retrieval errors you would likely see in open domain setting? And are existing multi-documents models sensitive to these type of errors? So this was a work that we basically tried to answer these questions. And so we start from existing multi-document data sets, because like, at least at the time, there was no data set that explores this pipeline end to end. So we tried to kind of operationalize this using existing multi-document summarization. The first assumption was we use the reference summary as the query. So because we don't have like queries of existing data sets with such queries. Reference summary is not great because it's like very verbose, but at the same time, it includes all the information that you would need to reconstruct the same summary. So it's kind of a fair assumption. And then we try to kind of simulate what type of retrieval errors you would likely to see. And our hypothesis was these are the major type of retrieval errors that you would see. So assuming that like you have a set of gold perfect documents, one retrieval error would be you just add additional document that is irrelevant. Or you might duplicate some of the documents, or you might change the order of the documents, which is kind of like if you have a different set of ranking. Or you might delete some documents that are important, or you might replace some documents, or you might paraphrase some documents. So these are typical types of retrieval errors that you would see. And now the question is, what documents we should perturb? So we chose different strategies, like we can actually randomly select documents to perturb, or we can choose, for example, the least similar, if you're doing deletion, select the least similar document to the reference summary. Or if you're doing addition, select the most similar document to the reference. And this mimics kind of a strong retriever. And we studied this on 5 different types of multi-document data sets across different domains. So we plot this using these charts, and you can see that the mean difference in summarization performance is plotted for each perturbation. And then we plot the random and oracle setting to kind of mimic the weak and strong retrievers. And we shade the differences larger than the average in red to show that, okay, these are actually significant differences. And here are the results. So each color is showing a different types of perturbation. You can see that models are generally insensitive to duplication. So it doesn't matter if you, for example, give the model multiple times the same document. It is kind of robust to this change. However, the models are sensitive to everything else. Like if you If you add more documents, if you delete some important documents, if you replace documents, all of them will result in declined performance in the model. And it turns out that these models are overly reliant on a few select input documents, which is also studied in another paper that came out before this work. So the answer is like the answer to the second question is like, yes, the multi-document summarizers are kind of sensitive to the input context. And the only type of perturbation that doesn't matter is duplication. So but how about the actual open domain multi-document setting? So we evaluate impact using an actual retrieval component. And then there are some questions to figure out, like how many documents you would retrieve using the retrieval. You can retrieve the maximum number of documents that you observe in each data set. Or you could select a mean of gold number of documents that you have, or you could assume that you know from before how many documents for each question you should retrieve. And this is kind of like an oracle setting. And at inference time, you don't have this information. So these are the results using retrieval. The first thing is like, how does the retrievers work? It is kind of different for each task. You can see that the retrieval performance can be anywhere from 22% recall at K and then up to 80%. And then we see that in this type of real-world retrieval setting, we see significant drop of performance on some of these data sets. The interesting thing is like the most of the drop in performance come from data sets like multi-news and WCEP. And we see less performance drop in some of the tasks like multi-X science or MS squared. It is interesting though, like we were curious why on data sets like MS squared, you don't see as much of a drop in performance. And MS squared is kind of a review generation data set. And we found that, okay, in this data set, actually, the task is very hard already, and the model is not able to use the input documents very well in the beginning. So if you change these documents, it doesn't matter because the model is not effective enough to use these documents. So the main takeaway is like if you have a stronger model that knows how to use the input documents, if you use it in a retrieval setting, you will see more drop in performance. So the question is, okay, can we actually address this with fine-tuning? So we took these data sets and we continued fine-tuning in this noisy setting. And we saw that for some of the data sets, the situation becomes better, and we could recover some of the performance that was lost. However, the recovery was very noisy and data set specific. Yeah, the problem still remains, as you can see in this figure. So the takeaways is like retrieval impacts the performance of these open domain multi-document tasks. It is possible to recover some of these errors, but LLMs are still very sensitive to this type of retrieval errors. And there are other types of work that kind of show similar findings. For example, this work from, I think it was CIIR last year, that showed large language models can be easily distracted by irrelevant context, or like this other work that showed how you can actually make them a little bit more robust to this irrelevant context. And there are some limitations with our work that this was only an upper bound because like we use reference summaries as queries. These were not relevant and these were not realistic queries. And because of this, we are unsure if you actually need multiple documents to answer the query. And this is actually a known problem in existing data sets on multi-document tasks. And this other paper showed that um, like if you consider most of the existing multi-document data sets, usually using only a few documents, for example, 1 to 2 or 3 documents, you can get a lot of coverage, and most of the information can only come from these few documents. So we need better benchmarks for multi-document modeling. An ideal benchmark should include information to address the query that come from more than one document. And these documents should provide complementary information, which is very difficult to design. So the last part, I want to tell you a little bit about this work that is kind of an attempt to study one task that could be also relevant to multi-document context. And this is the task of decontextualization. So in many applications, users need to refer to some snippets from a document. And this is very helpful for a lot of tasks, for example, for summarization, retrieval, attribution. And for example, you take a snippet from a document, and then you show it to the user. But this snippet can be confusing because you took it out of the context, and the snippet might not be standalone. So the task of decontextualization is actually rewriting this sentence using the context so that the sentence becomes interpretable without the full context. So this is a classic example. For example, Croatia at the FIFA World Cup. This comes from this page. Their best result thus far was reaching the 2018 final, where they lost 4-2 to France. And then if you decontextualize it, for example, you replace there with the Croatia. You replace like, for example, you use the word FIFA World Cup to make it clear that this was the FIFA World Cup competition. So now, if you check the decontext example, you can easily understand what's going on, whereas the above sentence was not very clear. So this is one of the important things that you need when you're reading papers too. For example, you see a lot of these statements like, whereas Epstein et al. Modeled hidden clampings, we use a method called alignment templates. And then your question is, what are these kind of concepts that this paper uses, or how is this cited paper relevant, and so on. So yeah, and then you also have this type of citations in scientific papers that kind of connects multiple documents together, which requires you to make this sentence kind of a standalone with context from other documents, which is exactly a multi-document setting. So how do actually people do this? Like we as scientists, if we are given this task, how we can do this? So there are some surface level edits that is pretty easy. Like in these surface level edits, for example, you replace a V with the authors, or like you replace pronouns with the actual references and so on. So this is pretty straightforward. There are some within document contexts that you need to extract. We found this to be kind of medium difficulty. And for this, for example, you need to see what are the earlier mentions of an entity, and then you kind of add that context to make it decontextualized. And the hardest type of decontextualization we found was multi-document context, where you need to contextualize a citation or a mention of a method or a data set or something with respect to another paper. And like through our expert human annotation, we found this to be very difficult. So the first question we were interested in is like, okay, these tasks are difficult, but can LLMs do this for us? So we use this type of prompts. We also use chain of thought prompting and all sorts of different prompting methods. And we found that like for easy surface level edits, LLMs are pretty good. They can actually decontextualize the snippets with a very good accuracy. However, we found that like for within document context, they might even hallucinate. They're not as good. For example, for some cases, they have a wrong mention of an entity or not a completely accurate description of some method. So this was a problem for LLMs. And in multi-document context, the situation was even worse. For example, they didn't understand what is the actual similarity between these papers. So they couldn't connect the exact information that you would need to contextualize that snippet. So the answer to this question is actually no, the LLMs cannot solve this task end to end. So our hypothesis was, can we actually break this task into multiple smaller steps using kind of a question answering framework? And this was actually formed by like talking to people, talking to scientists of like, if you're given this question, if you're given this sentence, how you would go about decontextualizing it. And we found that a lot of times people would start formulating questions like, for example, if I have an entity name that I don't know about, then my first question is, what is this? Or how does this relate to what I'm talking about, or something like this. So we did the same thing. We started by generating questions, and then using the question and the document and the snippet, we tried to generate answers and provide evidence for this answer. And then given the questions, the answers, the evidence, and the snippet, we give all of this to an LLM, and it would rewrite the original snippet for us to give us the decontextualized final snippet. And the hypothesis was, okay, breaking this task into these steps can actually help us. So the question generation could be things like this. For example, what is MLM plus BRLM, etc., and so on. The answers could be just description of like these entities. And the decontextualization is actually rewriting these into an snippet. And then we compare this decontextualization with the decontextualization that you would get from human expert annotators. Again, this pipeline is backed by a formative study where we had participants decontextualize text without, with and without these methods. And they usually found this to be much more helpful to decontextualize. And incorporating the cross-document information is highly context dependent. So for data collection, we use two types of context, the question answering and citation context. And then we ask a set of annotators to write questions. We ask another set of annotators to answer these questions. And we ask another set of annotators to rewrite these snippets. And for all of these, we use expert annotators that were hired through Upwork. So this is the details of the data set, and it includes a lot of like complicated decontextualization cases and about like 15% cross-document context. And yeah, so we see that this end-to-end performance is actually not great here. And the best performance that we get using our humans is like much better than the end-to-end performance. So now the question is, what's the best we can do if we completely follow our proposed QA pipeline? Like assuming we have the gold questions, the gold answers, and gold evidence, how does the model do? So we kind of did this experiment by kind of giving the model the gold questions, gold answers, and gold evidence to see which information is most useful. And then we explored different models. And what we found is, interestingly, just giving the model the question and answer yields to best results. And if you give the model other stuff, like the full document, the evidence, the performance actually is not as good. And it seems that the models are not very good at like navigating a very long context. So if you just give it a question and a gold answer and the original snippet, it can do the decontextualization much better than if you give it the full document. So yeah, this Oracle pipeline results in a much improved score compared with the end-to-end performance. However, in real scenario, we don't have any gold information. We don't know what are the right questions to ask and so on. So we wanted to see what happens if you use LLMs in all of the steps. So the first thing is we ask LLMs to generate questions, we ask LLMs to answer questions, and then we write to synthesize the results. And how does it work? It turns out that we get some improvements, but the task is kind of still difficult for the model under this decontextualization, under this decomposition setting. And we wanted to know why, what are the actual bottlenecks. So we did this study that we replaced the generations with gold human written generations. And we found that if you replace the questions with gold questions, you get a relatively big lift of between 48 to 73%. And if you replace the evidence, you would still see some improvement, but not as much. And the answers, like if you write the gold answers using human annotations, you get the highest lift. So we found that surprisingly, asking these questions and answering these questions is difficult for the models. They are not very good at asking the right questions that helps decontextualize a snippet. Or even if you're giving them a question within the context of a scientific article, they're not very good at answering those questions. And these are some type of errors that they make. So sometimes they disregard the instructions. Sometimes they provide some wrong answers. And sometimes you see some retrieval errors. They don't know what is the exact entity that you're talking about. And sometimes they just cannot answer the question well. And yeah, these are other types of information. So to recap, this decontextualization is a very useful task in practice, but we found it to be very challenging. It's kind of a task that is both single and multi-document. And we found that the decomposed pipeline can help LLMs do a little bit better, but doing this individual steps for the LLM is still difficult. And there is still a big gap with the gold pipeline. So to recap the whole talk, I hope I convinced you that there are many real-world applications that require multi-document processing, and this multi-document processing is a task that hopefully we will see more studies on in future. And we see that we need better benchmarks to study this task because a lot of the existing benchmarks are not perfect. And retrieval remains a challenge in these multi-document tasks. And the notion of relevance when you have like multi-documents is not as well defined. So with that, thank you so much for your attention. And I want to thank my collaborators for this talk. Thank you.
Thanks a lot for the very interesting talk. Quite a ton of information about multi-document modeling, summarization, question answering, and so on. So I think we have time for quite a few questions. Any questions from the audience here or online? James?
Hi, Arman. Thanks for the nice talk. I have a question about I think it was the middle of the talk, where you talked about how additions and deletions and swaps affected the performance of retrieval. One of the things you listed as a change that could happen was reordering.
Yeah.
But I don't think you evaluated the impact of that. So what I'm wondering is that because the multi-document summarization technology you're using doesn't pay any attention to the order of the documents, and so swaps wouldn't matter? Or is there some other reason that it was not looked at?
Yeah, actually, that's a good question. The ordering didn't matter too much, with exception of one data set. There was the data set WCEP on which the ordering change impacted the performance quite a lot, but the others didn't matter. And we actually digged into this a little bit, and it turns out that that data set was actually constructed by using a ranked order. So when they were like writing the gold summaries, they would use a retrieval system that ranked the documents, and then the human annotators would pay more attention to the initial documents. So that data set had some bias. And for that data set, we saw basically performance degradation when you reorder things. But for other data sets, it didn't matter. It turns out that the summarizers are good at figuring out information irrespective of the order.
Interesting. Thank you.
Thank you.
Hello, thank you for this great talk. I had a question about the QM10 model. I see that you generate the questions without any human involved. And my question is how, or if they had any effect in the quality of the generated questions had effect in the end performance or not.
Yeah, that's a good question. We didn't do any analysis with like what happens if you include a better quality questions. And I imagine if you would do it these days, you can just generate better questions with GPT-4. But again, our goal was to use a very lightweight model that gives you some like reasonable quality questions. And we did some manual investigation, and there were errors, but most of the errors were kind of readability errors, not kind of content errors. So for that, and because you're doing like larger scale pre-training, some level of noise is tolerable. But we didn't do any like thorough investigation of quality of the questions.
So I'll go and ask a kind of a more general questions. I have noticed that most of the work that you talked about were kind of targeting pre-training of the LLMs for these multi-document tasks or fine-tuning them for a task-specific goal. And nowadays we hear a lot of buzz about the alignment stage in training LLMs, like RLHF and so on. I'm wondering, what are your thoughts on the impacts of alignment stages in multi-document modeling?
Yeah, that's a great question. I think one area that might be interesting to study alignment in the context of multi-document modeling is where you would collect data that is kind of relevant to this multi-document context, and then you do preference optimization on that type of data. Like, for example, you could imagine having data that, for this decontextualization work, for example, you can have data that can better connect multiple documents together, or like add context from the other document. And that one would be more preferred to another data point that you generate using just a single document. And maybe using alignment methods like RLHF or DPO on that type of data would make the models a little better than like baselines on these multi-document tasks. Yeah, that's an interesting question. I haven't seen anyone investigating that, but I see some opportunities that you can basically kind of adapt similar approaches to create synthetic preference data for multi-document tasks.
Yeah, I agree. I think the reason I asked that question was perhaps when you deal with multi-documents, it's pretty challenging to get human preferences. It's time consuming. And maybe we have to rethink how these alignment stages work when we deal with such long context.
Exactly.
Yeah, thanks for insights. Any other questions from the audience here or online? So I'll ask the final question then. What are your thoughts about query-focused multi-document summarization? So coming from the IR background, users are interested in specific kind of aspects of documents, but they have some information needs. They have queries. So you did have this retrieval augmented approach for summarization. But at the end, the way it's been evaluated is not just how it is related to the query, I think, or at least the queries were synthetic from the references. But in general, in query-focused summarization, so two different queries might result in the same set of retrieval results, but the summarization could be different. And do you think that anything we are building here needs to be revisited for these kind of tasks?
Yeah, no, that's a great point. Again, one of the limitations of this study was that like we just use reference summaries as queries, and like because there's like no kind of data set that at least we were not aware of any data set that existed that kind of supported this task. One difference with like query focused summarization in general is in this type of open domain, you have a very large document index that you first need to find which documents are relevant to a query. But in classic like query-focused summarization, you are usually given the documents, and then the goal is to summarize those documents with respect to that query. But yeah, it becomes a very interesting question of like, what happens if you have queries that are kind of very nuanced and like the differences between them are very like you kind of can include instructions in your queries that like from the content standpoint, they ask for the same documents, but like the instructions that you have or a specific type of generation that you want them to do are different. And then you would see how the models would react with this. Yeah, I think the bottleneck is still, and this is my own like a speculation. It's not like backed by any data, but I still think the bottleneck should be in retrieval, because like understanding the intent of these complex queries can be difficult. And like if you have the right documents that you retrieve and you give it to the like the LLMs are so good these days that they should be able to utilize the right context if they are given. But yeah, that's a very interesting question.
Well, thank you so much. So let's thank the speaker one more time.
Thank you.